Hi, welcome to another session of control systems. In today's class 2 under time response analysis, we are going to see the basics which are involved with first order system as well as second order system. In our first class under control system, when we are dealing with time response analysis, we have seen the response of first order system. You remember we had gain of the system, you had the feedback of the system, and this system has a closed loop transfer function given by g of s by 1 plus g of s h of s, and this is also known as the transfer function where we have c of s as output and r of s as input. And we have also seen that R of S is the input signal, and control system standard test signals are used as input signals. What are those test signals? Step signal, ramp signal, parabolic signal, and impulse signal. Also, we have seen the response of step signal as well as unit step signal, where you have R of t is equal to A for step input and R of t is equal to 0 for different values of t greater than 0, sorry, t greater than or equal to 0 or t less than 0, and if at all it is replaced by a equal to 1, then this is how the waveforms looks like. Similarly, we have seen the output response of ramp signal, then parabolic signal and impulse signal, and also we have employed the unit step input for first order system where g of s is replaced by 1 by st and h is replaced by 1, and this is how the system got changed with the input as 1, that is time domain input. The frequency domain input changes to 1 by s, and we remember the formula of transfer function, that is c of s by r of s is equal to 1 by st by 1 plus 1 by st. The simplification we have done, and we have employed r of s is equal to 1 by s, and the transfer function changed to the output c of s values as a by s plus b by s plus 1 by t. And with the help of partial fractions, we got the value of a, which was 1, and b, which was minus 1. Just we substitute the values of the a and b constants and applied inverse Laplace to the above equation, and we got the value of c of t as 1 minus e to the power of minus t by tau. Tau is the time constant. And what was the conclusion made? Per unit step input, when it was applied to the first order system, we got the output as exponentially rising curve. So this was the conclusion made with the time response analysis for class 1. In today's class, we are going to see about the second order system. This is the representation of a second order system where you have input R of s, output as C of s, and you have a unity feedback gain. In fact, when you employ G of s with the value of omega n square by s square plus 2 zeta omega ns and H of s value with 1, you are going to get the original transfer function for the second order system. So this is how we got the transfer function, that is omega n square by s square plus 2 zeta omega ns plus omega n square. It's a very important representation of second order system where you should know that omega n is known to be undamped natural frequency, and zeta, this is known as damping ratio, where it is defined as the actual damping to critical damping. What are all those things? We are also going to learn in our further classes. First, let us see the characteristic equation of second order system. Based upon the zetas, first the system is classified into undamped system where you have zeta equal to 0, then underdamped system where you range the value of zeta from 0 to 1, then you have critically damped system when you substitute zeta equal to 1, and you have overdamped system when zeta is greater than 1. So individually we are going to see the cases. First, let us concentrate on the characteristic equation. The denominator of the transfer function gives us the characteristic equation given by s square plus 2 zeta omega ns plus omega n square equal to 0. This is in the form of a square plus 2ab plus b square. So you can easily find out the roots for this characteristic equation represented by s1 and s2. by the formula minus b plus or minus under root of b square minus 4ac by 2 into a. Just have substitute the values, and we can get the values of roots to be zeta omega n plus or minus omega n under root zeta square minus 1. So remember, these kind of roots are obtained for the second order system, and later on by substituting the value of zeta we can easily estimate exactly the location of the poles, or we can talk about the stability of the system. Anyhow, let us go with the individual case. First, let us go with the response of undamped second order system per unit step input. Like in the previous class under time response analysis, class 1, we have seen the response of first order system per unit step. Now we are going to see the second order system when the zeta value is 0. So the standard form of second order closed loop transfer function is given by C of s by R of s is equal to omega n square by s square plus 2 zeta omega n s plus omega n square. And we need to remember that undamped system indicates zeta equal to 0. So substituting in the above transfer function, we are going to obtain omega n square by s square plus omega n square. Just we have substituted the value of zeta equal to 0. Then the above transfer function changes to below transfer function like this. Now the input is given to be step input, that is R of t is equal to 1. Then R of s is nothing but 1 by s. Substituting the R of s over here in this transfer function, and the response in s domain of response is obtained as C of s is equal to omega n square by this R of s is, when it goes to the right hand side, it becomes 1 by s into s square plus omega n square. Now with the help of partial fraction approach, we need to find out the value of constant a and b. So that you can do by taking a value and multiplying the transfer function which is given, that is omega n square by s into s square plus omega n square multiplied with s. The s and s term over here, they cancel out, and we have to substitute the value of s is equal to 0 in order to obtain the value of a. So we are going to do that, and we are going to get the value of a as 1. Likewise, take the transfer function, multiply with s square plus omega n square, and substitute s is equal to j omega n. And when you are going to do that, you are going to get in the numerator omega n square by denominator you have s, that is replaced by j omega n. The omega n and omega n cancels out, and this becomes omega n by j. If at all I take the j onto the numerator, it becomes minus j omega n. This is nothing but s value. So in fact, b changes to minus s. Now once a and b are obtained, we are going to substitute in the transfer function of frequency domain is 1 by s minus s by s square plus omega n square. What we need to keep in our mind is that we should know what is Laplace transform and inverse Laplace transform. Inverse Laplace transform of 1 by s is equal to 1, and inverse Laplace transform of s by s square plus omega n square is equal to cos omega nt. Now in this equation, by applying inverse Laplace, we are going to get c of t to be 1 minus cos omega nt. Now we got the output response. So input is step, and output you are going to obtain, just you substitute the value of t as 0 degrees, 90 degrees, 180 degrees, and repeat so on. You are going to get the graph of the output, which is in this oscillations form. So you can see the oscillations, they keep it on repeating. In fact, I can say this is the constant oscillations. So this is the response of second order system under undamped condition when it is taken, that is the zeta value is taken to be 0. Likewise, you can apply impulse as input, and you can check out the output, and later on you can apply the parabola as input, and you can check out the output. In our next class, we are going to see another condition of zeta, where you are going to substitute the value of zeta to be equivalent to 0 in this case, and in the next case we are going to see zeta equal to 1, and later on we are going to range the value of zeta from 0 to 1 and above 1. So I hope you like this particular session. Please share among your friends and subscribe to this channel and press the bell icon for future notifications. Thank you.